Hello my dear students. Today we are going to continue with our topic solutions, and we are going to study today the colligative properties. But before we come to that topic, we have some important things left. First is the composition of binary solution in vapor phase. Now this is one formula that you have to learn. This Ya and Yb are the mole fraction of the components in the vapor phase. If you have to calculate these, suppose in the question in the exams they ask you to calculate the mole fraction of that component in the vapor phase or in the gaseous phase, in that condition you have to put this formula, that is Ya equal to Xa multiplied by P naught A upon P total and Yb equal to Xb multiplied by P naught B upon P total. Let us solve one question based on the previous knowledge. Question is 30 gram of urea whose molar mass is 60 gram per mole is dissolved in 846 gram of water. Calculate the vapor pressure of water for this solution. If the vapor pressure of the pure water at 298 Kelvin is 23.8 mm Hg. So first of all, you see here, what do we have to calculate? We have to calculate the vapor pressure of the water for this solution. Now how do we calculate this? First of all, let us find out the number of moles of urea and number of moles for water. So suppose we take the solute as 2, so that's why we'll find out first of all N2. So finding N2, it will be equal to W2 upon M2, that is how much, 30 upon 60, and this is nothing but 0.5. Similarly, finding out N1 is 846 upon, and what is the molar mass of water, that is 18. If we calculate this, we get 47. So this is the 0.5 mole and this is the 47 mole. Now this is the first thing solved. Now we have to calculate the vapor pressure of water. What we are given? We are given the vapor pressure for the pure solution, so pure water, that is we are given P naught A. Suppose this is NB and this is NA. Now we are given P naught A. P naught A is 23.8 mm Hg. Do you know what is the formula of P naught A, or what is the formula of PA? The formula for PA is P naught A Xa. Now we have to find out this PA only because it is written that we have to calculate the vapor pressure of water in this solution. So we have to find out this PA. Putting the value of P naught A as 23.8 multiplied by Xa, which is the mole fraction, that is Na upon Na plus Nb, we get 23.8 multiplied by 47 upon 47.5. Now if we solve this, we'll get the vapor pressure of pure water for this solution, whatever we solve it, mmHg. This is the vapor pressure of water for this solution. Now we'll see one more question from NCERT. The question says the vapor pressure of pure A and B are 450 mmHg, means this is P naught A, and 700 mmHg, which is P naught B. Find the composition of mixture, means you have to find out Xa, you have to find out Xb, and the composition in the vapor phase. If the total vapor pressure is 600 mmHg, so this is Pt. Now you know one thing, that Pt is P naught A Xa plus P naught B Xb. We already know this, we have solved this, we have also calculated the vapor pressure in our previous class. Now what can I write instead of, suppose, Xb? Instead of Xb, what I can write is, we can write instead of Xa. What can we write? Means we can write like this, that Pt equal to P naught A 1 minus Xb plus same term. Solving it, Pt equal to P naught A minus P naught A Xb plus P naught B Xb. Putting the values, Pt is 600, P naught A is 450 minus what is the value of again P naught A, that is 450 XB, plus what is the value of P naught B, that is 700 XB. Now we'll make a partition. We'll solve further thing over here. So solving it, what do we get? We know this thing that we'll send this over there, so we'll get here, when we subtract this we get 150 equal to, and while we solve this, so we get 250 XB. So what are we getting XB? We are getting XB as 15 upon 25, which can be written as 3 upon 5, or when we solve it we get 0.6. So what will be XA? XA will be equal to 1 minus XB, that is 1 minus 0.6, it will be 0.4. So these are our two numericals. Now let us see the next topic of this chapter, that is colligative properties. Colligative properties are those properties for only ideal solution where these properties depend upon the number of particles of solute. Now these are only the properties which mainly depend on the number of particles, neither on the nature of solvent, neither on the nature of solute, neither on the chemical properties, only the number of solute. So suppose we have two very different solutions. Suppose we have one solution of acetic acid and one solution we have of, suppose, sodium hydroxide. Or let us not see this, let us see some weak things like acetic acid is there and ethyl acetate is there. Now if suppose these two contain the same number of solute particles, in that condition the colligative properties for both of these will be same. So these depend on the number of particles of solute and not on the nature of solvent. These are applicable to ideal solution only, or those solutions which are very dilute, because we know when we dilute the solution we can get or we can achieve nearly ideal state. There are four colligative properties to be discussed, that is relative lowering of vapor. The second colligative property is elevation and boiling point, third depression and freezing point, and the fourth is the osmotic pressure. We have to discuss these four colligative properties. These four colligative properties are there in our syllabus. Now today we are going to start with the first two colligative properties. This first one, that is the relative lowering of vapor pressure, and the second one, that is the elevation in the boiling point. So let us start them one by one. First of all, we'll see what is the meaning of relative lowering of vapor pressure. Now suppose there is a binary solution. Binary solution means two components and there is one component which is non-volatile solute. In that case, what will be our P total? P total is Pa plus Pb, which can be further expressed according to Raoult's law as P naught A XA and P naught B XB. Now since one is non-volatile, that is B, so P naught B will be 0. In that condition P naught B XB will also be 0, so that whole term becomes 0. We are only left with P naught A XA. Further on, when we solve this, instead of XA we can add 1 minus XB. That means P total equal to P naught A minus P naught A XB. Sending this P total there means when we interchange these terms we get P naught A XB equal to P naught A minus P total. Now this P naught A minus P total becomes delta P. This delta P is only the relative lowering of vapor pressure. Now if I send this P naught A down to this delta P, what do I get? In that condition I will get such term where I have delta P upon P naught A equal to XB. This term is known as relative lowering. The lowering in vapor pressure is denoted by delta P. Now you can see easily here also that this relative lowering is directly proportional to the mole fraction of solute, and that's why we can say that the relative lowering of vapor pressure depends upon the mole fraction of the solute component. That means greater the amount of non-volatile solute present in the solution, greater will be its lowering in the vapor pressure. Now there are some applications for the relative lowering of vapor pressure, that where can we use this colligative property. The first application is, or the main application is, to determine the molar mass of solute. in the case of dilute solutions. So this is the first case that we have to calculate the molar mass of solute for the dilute solutions. Now you know dilute solutions are the ideal solutions. We know that delta P is always equals to P naught A XB, as we have seen over here, that is delta P equal to P naught A XB. Now suppose if I send this P naught A down in this way, I get this, which I have written here also. Further on, what do I do is that if instead of this XB I express in the terms of moles, I get NB upon Na plus Nb. Now because it is a dilute solution, the solute concentration will be very less. Nb will be very less as compared to Na. So I can ignore this term. So I will get delta P upon P naught A equal to, this term will remain because it is in the numerator, but the denominator term can be neglected, as we did in the questions of equilibrium previous year. This Nb is removed. Hence delta P upon P naught A equal to, now instead of his Nb I can write Wb upon Mb, instead of Na I can write Wa upon Ma. So relative lowering becomes this term for the dilute solutions. Now what I was saying in the application, that we can calculate the molar mass of solute, that is Mb. So Mb is here, so send it on one side and keep other things on the one side. So Mb will be equal to Wb into Ma into P naught A upon delta P into Wa. This is the condition for calculation of the molar mass of solute in the case of dilute solutions via relative lowering of vapor pressure. There is another also, where we have when the solution is not dilute. You can learn this. If the solution is not dilute, so we will not neglect that Nb, and then when we solve it we get Mb equal to Wb into Ma into P total upon P naught A minus P total, this is delta P into Wa. This is our next second formula. Now let us see one question. Vapor pressure of the pure water at 298 Kelvin is 23.8 mm Hg. So this is the vapor pressure of pure water. Water is a solvent, so it will be P naught A. 50 gram of urea, that is CONH3 whole twice, is dissolved in 850 gram of water. Then calculate the amount of vapor pressure of solution and its relative lowering. So this CONH3 whole twice. Now first of all we have to see that what is the molar mass of this CONH3. So if I add this is 12 plus 16 plus 2 into 14 plus 3. So it will be 12 plus 16. I can directly write it that it will be 28 plus 2 into 17. This is 34 plus 28. It will be 62. So 62 gram per mole is the molar mass of urea. Now we will calculate Nb. Nb is given mass, that is 50 gram upon 62. Similarly Na will be equal to 850 gram upon 18. We have to calculate the vapor pressure of solution, that is we have to calculate P total and its relative lowering. How do we calculate P total? Because this is a non-volatile solute urea, we have P total as P naught A XA only. The second term becomes 0. Instead of XA, I can add Na upon Na plus Nb multiply by P naught A. Now we will solve this. What do I get? Now here I cannot neglect this term because we are calculating the mole fraction. In the case when this was the colligative property, that time we can neglect this Nb. Now we'll solve this Pt. Other case we have to solve is delta P upon P naught A. That is the relative lowering that we have to calculate. What it will be equal to? We know it is equals to Xb, that is it is equals to Nb upon Na plus Nb. If you calculate this term, you will be easily getting the relative lowering also. So this is the question and how it can be solved. With this, our relative lowering of vapor pressure is over. Let us see our next colligative property, that is elevation of boiling point. This is represented as delta Tb. Now what does it mean? See, delta TB is the difference between the boiling point of solution with the non-volatile solute and the pure solvent. What are they saying? The colligative property name itself says that elevation in boiling point, which means that the boiling point is elevated. And we are also writing here non-volatile solute, so it means that when we are adding non-volatile solute in the pure solvent, then somewhere or the other the boiling point is elevated. That is only the elevation in boiling point, represented by delta TB. So delta TB is a difference because it is delta. It is equals to TB minus T naught B. T naught B is the boiling point of pure solvent, which is lesser, and TB is the boiling point of that solvent where we have added the non-volatile solute, which will be greater. Now, what is the reason for elevation in boiling point on addition of non-volatile solute? This can be easily solved by our previous colligative property by relating to that. We have discussed that when we add non-volatile solute, the free surface of the solution will have lesser number of volatile component. That's why it will produce less vapors, and hence at that 100 degrees Celsius, suppose we take water, so at 100 degrees Celsius when it was easily evaporating, now because some part of the surface has been occupied by non-volatile solute, so it will not be evaporating enough, only half of the surface will be available. Now to attain that much evaporation we have to heat it more, means we have to heat at greater than 100 degrees Celsius. So what we are doing, we are elevating the boiling point. So reason is, it is due to the lowering in vapor pressure, because when we add non-volatile solute to a pure solvent, its vapor pressure will decrease, and now to attain the same vapor pressure we need to boil it more, and hence it leads to the elevation in the boiling point. So we can say that whatever it is written here, it is easy to understand. Now we will see this graph. This graph shows the relationship between vapor pressure and temperature, that as we are increasing the temperature, our vapor pressure is increasing, means more and more vapors are formed. For this temperature increase, certainly in the case of pure solvent, you see that at a very smaller temperature also we can have more vapor pressures. At this point we have this much vapor pressure at a less temperature, but now if it is a solution and we have non-volatile solute, so we have to heat it more, we have to give more temperature to attain the same amount of vapor pressure. So we have taken more temperature. So this pure solvent, its boiling point and the solution boiling point, that difference is delta TB, which is actually elevated. Similarly, the pressure at the point when this was solvent had attained its vapor pressure, at that time what was the solution point? Means suppose at 100 degrees Celsius the water gets evaporated. Now we have a solution where it is not evaporating at 100 degrees Celsius. So now at 100 degrees Celsius, what is the condition of solution? This point and this point is delta P. So we can say that delta TB is directly proportional to delta P, means more is this elevation in boiling point, more will be the pressure difference. This is easily understood from the graph. The second thing that we know is delta P is directly proportional to the mole fraction. We have already seen in the previous colligative property. By these two, we can say that delta TB is directly proportional to XB, which says everything very clearly, that more is the mole fraction of non-volatile solute, more will be the elevation in boiling point. When we remove this proportionality sign, we get Kb. This Kb is known as molar ebullioscopic constant. Now this is Xb. In Xb, what can we write? Instead of this Xb, we can add Nb upon Na plus Nb, and we are discussing the dilute solutions because we have to see the ideal conditions. In that case, the solute concentration is already very low. We can ignore this Nb, so it will be Nb upon Na. Substituting this Nb upon Na with Wb upon Mb and Wa upon Ma, we can get this kind of equation. Further on, if I see this, what is it? It is molality. Molality is what? Molality is the number of moles of solute upon the mass of solvent in kg. If we don't write kg and we write gram, we have to multiply by 1000 also. So it is kb into ma into molality. So that is the elevation in the boiling point. So if we say that molality is 1, suppose in that formula we have molality 1, in that case we'll write delta Tb equal to Kb into 1. So delta Tb will become equal to Kb. Now suppose if you are asked to define molar abeloscopic constant, then what it will be? We can easily write that molar abeloscopic constant is equals to, or molar abeloscopic constant is defined as the elevation in boiling point for 1 molar solution, because this term turned into 1. Then we can easily equate these two. The unit of this abeloscopic constant is Kelvin per molar. Why? Because when we send this molarity term down, we have this temperature term is Kelvin upon molar. Now let us see the application of this colligative property again to calculate the molar mass of solute. So it is used to determine the molar mass of solute, and the formula is very simple. We know delta Tb equal to Kb into m. Instead of m we can write Wb upon Mb into weight of solvent in kg we required, but here it is gram, so we put 1000. Solving for this Mb we get Kb into Wb into 1000 upon delta Tb into Wa in grams. Let us see one question. Question says boiling point of water at 750 mm Hg is 99.63 degrees Celsius. So this is at this pressure. How much sucrose is to be added to 500 gram such that it boils at 100 degrees Celsius? So the boiling point is elevated. And what is delta Tb? Delta Tb is nothing but subtraction of these two, that is 100 minus 99.63. Solving it, what do we get? We get 0.37. Now we have already one thing, that is we have here Kb given. Now we have to find out that how much sucrose is to be added. We have to find Mb, what mass of sucrose is to be added. Putting the values, Kb is 0.52 into Wb. What is Wb? Wb is already given, that is Wb is the Wb is what? Wb is the mass of sucrose that we should know, that is 342 into 1000 upon delta Tb, that is 0.37, multiplied by Wa, which is given as 500. Solving this will get our answer. So in this way we can solve this easy question.